Okay, how do we know the information in Section 1? Well, it's done through various stages. The most important one you've probably heard of already and worked through a little bit of GCSE. That was the alpha scattering experiment completed for Rutherford by his two students, Geiger and Marsden. Okay, so this is the first kind of evidential research done at this stage on particles, and a lot of the original work came out of Manchester University. They still have the same lab there. Crucially, basic ideas of this we need to know our way around because it links into what we've already done with fields. Okay, so bit of a recap. We'll go back through the main bits in the lesson, but his two students looked using a scintillator, so it's something that every time a particle hit it gave a little flash of light on the end of a microscope, and what they did was over time they kept a radioactive source firing at the gold leaf, and they moved the detector to different angles and just literally counted in a set time how many flashes they saw. Long, slow experiment, but what they did was found some fairly interesting facts. They found that most of the particles that came through the gold foil pretty much came in a straight line. But Rutherford suggested they actually flip all the way round and start looking on the back as well. And what they realised was actually some of them were deflected right back. So it was what put to bed the idea of the plum pudding model, the Christmas pudding model. So the idea that electrons that had recently been discovered were just kind of spread throughout some sort of nuclei dough, an atomic dough, and it led us to this picture instead. Okay, with a little bit of tweaking became the Bohr model of the atom. So artistically down the side here gives you some sort of scale. The nucleus is actually way smaller than this. The way to do it is to actually play with the idea on PHET. So again, I'll just put up here, if you haven't gone to it already, go and look at Rutherford scattering or alpha scattering on the PHET website. Okay, slight typo, just highlight for you there. Okay, what did they do? Well, they found that most of the particles went on. Okay, what does that mean? Well, it means there's nothing much slowing them down. That on its own isn't a conclusion. However, when we start looking at the other details, we get a bit more to it. By looking back at the top, or on the reverse side, they found that almost about 1 in 8,000 particles, alpha particles, deflected straight back. Okay, or for them, actually less than that, deflected more than 90 degrees, so effectively we're bouncing off something. Okay, so a reasonably small amount, but if we consider how much actually bounced straight back, it's even smaller. So by sussing out what's going on in here and why it's happening, it managed to actually calculate roughly the size of the nucleus. Okay, and we'll do that calculation. So let's break down the facts themselves. So we've got very few of them are deflecting back. What does that mean? Well, the thing that is causing them to come back is very small. Most of it is not having an effect. So we have a very small nucleus. Okay, and it was called the nucleus because of that central position, that fact that it almost didn't seem to exist anywhere else. So that means that conversely, it's almost empty in the atom. Okay, so it's mainly empty space. But that's your definition. So it's a very small nucleus. That's the actual meaning. Let's put that in brackets just to highlight that. Try not to use that in the exams. Okay, the second thing is that it deflected the alpha particle and it had a lot of momentum. It was fast moving. Okay, which means one of two things. The fact that it deflects means that that's got quite a lot of mass. The fact that it has a lot of momentum, that means that has a huge mass. Okay, so it's about that restoration of momentum. That momentum may be passed on a little bit, but actually most of it is retained by the alpha particle that deflects off it. So basically the whole mass, by their calculation, or 99.999% of the mass of the atom is concentrated in the nucleus. Okay, so it's hard to move. That's not moving anywhere, therefore it must be massive, and therefore things deflect off it rather than that knocking the nucleus out. The fact that they repel, okay, so that's about the fast moving alpha particle, that's the one about the rarity of it. The fact that they repel shows that quite simply, the nucleus is positive. Why? Because we know that we know that the alpha particle is positive, therefore the alpha particle deflecting from it must mean that that is positive as well. And the last thing can be indirectly implied for that. We know that the atoms, the gold atoms that were in there, were neutral. So we need negative charge elsewhere. So where else is it? Well, the only conclusion that comes from that is the other things aren't having any effect, so they are tiny in comparison. So tiny negative charge, or charges, are basically thinly distributed elsewhere. So they're not in a lump. You could tell, otherwise you get deflection off that. Okay, so by the mathematics of it, they found that there is no effect going on here or anywhere else other than the nucleus. So these must be distributed. They're not forming a negative nucleus somewhere else. Okay, now it does give us a bit more hint on other things as well. The fact that you've got a positive charge in the middle and yet it changes with different atoms means that this can't be solid, and therefore how can all this repelling positive charge not throw itself apart, not fall apart? So that does give a hint that potentially there are other particles inside. Okay, so we'll just put in that hints there, so the hints of other particles in the nucleus. And because we found out later by Chadwick, or Chadwick found out that they are neutral, they were really, really hard to discover. So a lot of work was carried on with atomic research before the discovery of the nucleus, the neutrons in the nucleus. So they are fundamental to the story. They're the fundamental particles of radioactivity. We'll come back to that later, but they don't feature in the scale picture. So those are the basic qualitative descriptions. We need to go a bit deeper. And we go in deeper in terms of the mathematics that Rutherford did. And you've already done these, but it actually took Rutherford about 11 years. He actually came out of a World War I meeting because he realised the importance of it, the doodling on it. Okay. So, what is all this about? Well, he decided he'd take the mathematics of those particles that are shooting and bounce pretty much straight back. Okay. So he realised they don't go and collide off them, but they'll get in, they'll have a certain amount of energy, they'll lose energy as they come in, they'll stop, and then that repulsion will bounce them back again, repel them away, accelerate them off into the distance. So how does it all work? Well, it's point charges. Okay, so the mathematics of it is fairly straightforward. What he realised, as I said, all of that kinetic energy had been converted or transferred into that electrical energy, that potential energy of the nucleus here. So we need to think about the potential around our charges as it comes in, reaches that maximum potential, and then goes back out again. Okay, so how does it work? Well, fairly straightforward. It's what we had already. So if we're talking about kinetic energy, we know that the kinetic energy, or let's say the change in kinetic energy, is the change in electrical energy. Okay, not electric field strength, just be wary, electrical energy. So that is going to equal the idea of Q times V. Okay, so the potential at this point, there's our value of V. Okay, or rather the maximum V. We're working on the assumption that if you're firing it from far enough away, then the potential is zero. That electrical energy is zero. So it's just a case of putting the numbers in. We know that the potential at one point comes from our calculations of point charge electric field. So our field radiates around our nucleus, and therefore we can work out the potential at a distance from it. So I'm just going to keep with this notation, but we'll put the calculation in here. So what is the calculation for potential? Well, 1 over 4 pi epsilon. I should say he realised it was a vacuum. To do the experiment, they realised they actually had to evacuate it anyway, so the gold leaf was surrounded by as best a vacuum they could get at the time. So he realises there must be a vacuum in the middle anyway. The charge that's in the middle and divided by, you got it, R. Okay, so not R squared, that's forces. The one to do with energy and potential is R itself. So what you can do is rearrange that around a little bit. We're not going to go into this because alpha particles were really known. We know very much, they're very distinct. They have a very distinct level of kinetic energy, 5 mega electron volts to be almost precise. So what we can do is we can find that around. We're going to just going to use capital R because I've just put capital R over there. So if we rearrange that, then what we can find is very simply put some numbers in, rearrange a little bit, and we just go with 1 over 4 pi R, 1 over 4 pi epsilon, so 9 times 10 to the 9 roughly, multiplied by Q, bring the 2 together, divided by that kinetic energy. Okay, so maths is simple, and any questions you may get on this in the exam are simple. Energy change equals energy change. However, we need to know what the charges are, and chemists have done all the work on that, so that's quite simple. It was this bit it's where it started to get interesting. So give me some values here. Okay, now I will just put in that translation there. So EK equals 5 mega electron volts. That means 5 times 10 to the 6 times by Q. Okay, where Q is E, the charge of an electron. Okay, so that fundamental charge. Okay, now I'm going to put Q in exclamation marks for a reason, and the reason is we need to think of it in terms of E. So I'm actually going to keep it simple because most of our stuff works around the value of E. We'll do it that way. I know in your data books it's not, but if I put it like that, then what I can do is use this calculation in a slightly cleverer way, i.e. keeping the math simple. So 1 over 4 pi epsilon still. Okay, what is our charge on our particle here? Well, for gold, Z, the proton number is 79, so it's 79 lots of E. Okay, we then going to multiply by the incoming charge Q, which is for an alpha particle 2 protons, so that's 2E. And then if we use this, you can see that the E's cancel out. It makes it a lot simpler. So 5 times 10 to the 6 E, and we can just simplify that a little bit. And if we put the numbers in, what you'll find is that gives us around about 45 femtometers. Now they knew at the time that the size of an atom was around about 10 to the minus 10 meters. This is 10 to the minus 15. This is an astronomically small value. Yeah, and if you think about what that means in terms of our picture, then you'll start to see why I was talking about peas in the centre of football stadiums. Okay, it's around about 10 to the 5 times smaller than the whole of the atom. So if I took this picture on your page, this is a very small segment of the atom. You know, my page would near enough, for that size, near enough be the size of the stadium down in Barnsley. Okay, it would be the width of the pitch, roughly. It's tiny. Okay, and it's that tiny little thing that deflected these high-speed particles. Now 5 megaelectron volts is actually around about alpha particles travelling around about 95% the speed of light. They're really, really fast, and yet they just bounce off these tiny little particles. So massive, but small, really dense. And that's quite an interesting thing, which leads us into other sections. Now I'll leave it at that for today, because this is not actually right. Okay, it gives us an estimate of the scale. Unfortunately, to make it get closer, to give a more accurate value of R, we need to make this go faster. So we take our alpha particles, and then, like Cockcroft and Walton, basically when they invented the Van de Graaff type machine, they accelerated them in and was born the whole research area of particle accelerators. If you make it go faster, we get closer and closer. Unfortunately, if you put protons and neutrons near a nucleus, they get subsumed, they get absorbed by that, or we cause nuclear reactions. Okay, and things change. So using alpha particles, we know now, is not a great way of doing it. So we use different systems, and this is where we start to use things like electrons, because electrons won't get absorbed by a nucleus. Okay, it's not going to have the same effect on protons and neutrons. We'll come back, there is a subtle case where it's slightly different, but that's a one-off case. Okay, so we use other methods to make it happen.